Hello everyone, welcome back to the Aspen Tech channel, and we are bringing our lecture number 103 on this channel, which is focused on the simulation and design of plug flow reactor. We have obviously solved plug flow reactor in Aspen HYSYS and in Aspen Plus, but that were the very fundamental or basic examples, concepts, and now we will be solving a bit complex version of it. So if you have not subscribed yet, please do subscribe the channel and click the bell icon to get all updates related to this channel. So we have been given the system which is that ethane converts to ethene and hydrogen. So we can say it as ethane dehydrogenation process in which it is converted to ethene and hydrogen, and it's obviously an endothermic process. And so far the conditions given for this process are that activation energy is equal to 82 kilocalories per kg mole. The pre-exponential factor is 0.072. The rate unit is kg mole per cubic meter second, and basis unit is kg mole per cubic meter. So this is the information which is relevant to Aspen HYSYS, and all of the parameters is provided over here. And if we are dealing in Aspen HYSYS, then obviously we have to select one of the three, which is heterogeneous catalytic, kinetic, or simple rate. And accordingly, once you are going to Aspen Plus, you have to select power law, Langmuir Hugel-Morrison equation, or so on, whichever is your requirement. So accordingly, based on these conditions, we will specify our reaction kinetics, and accordingly based on the conditions which will be given in the upcoming slide, we will calculate the conversions, and accordingly we will do the simulation in the process and design as well. The feed specification include temperature of 1100 Kelvin, pressure of 680 m. The feed flow rate is 1000 kg mole per hour with pure ethane feed in the system, and the reactor specification as initial guess given as length is equal to 10 meters, diameter is equal to 3 meters. It's an isothermal reactor, means the feed temperature and the product temperature should remain the same. Obviously, we know that we can use either set tool for it, or we can simply specify as well. And we require 80% conversion of ethane. So first we will see that based on these two diameter and length conditions, can we achieve this conversion? If yes, we will stop our simulation task over there. If no, then we have to use some other parameters like adjust tool and so on. So let's quickly go to Aspen HYSYS and simulate this process, obviously design the process as well. So quickly adding the components ethane, ethene, and hydrogen. Ethylene is obviously ethene, hydrogen is added as well. So fluid package to be selected in this process is Peng Robinson, and accordingly the minimum required information is complete. But since reactions are already involved, so click on this reactions, click on this add reaction. We can choose either heterogeneous catalytic, kinetic, or simple rate because it's a forward reaction only. Once this is a reverse reaction, then we have to be very careful in choosing between these three systems. So clicking on this kinetic reaction and double clicking on it, and we know that ethane, ethylene, and hydrogen are involved. The stoichiometric coefficient for ethane is -1 because it's a reactant. For ethylene and for hydrogen, it will be 1 because these are the products. Forward order, obviously, it's completely dependent on ethane, so obviously it should be 1 and other should be 0. While there is no reverse reaction, so all of these will automatically be 0, or we can simply label it as. Molar concentration is basis, base component is ethane, reaction phase is vapor phase reaction, conditions of temperature will remain the same, the basis unit is kg mole per cubic meter, and the rate units is kg mole per cubic meter second. So in the value of A, which we will specify now, 0.072, for it is 82 kilocalories per kg mole, and the minimum required information is completed over here. And now this reaction set is ready. So we will close it and we will add it to the fluid package. So add set to fluid package. And now going to the simulation environment, and we will select the plug flow reactor over here, and we will place it over here. Double clicking on it and giving the required connections, feed, product, and obviously we have to give the energy stream because we want that it's an isothermal reactor, no change in temperature. In reactions, specifying the reaction set, unknown dimensions, 10 meter is its length, 3 meter, diameter unknown duty, obviously it's not solved because we have not specified feed conditions. So 1100 Kelvin, then 680 m, 1000 kg mole per hour, and it's a pure ethane, while other ethylene and hydrogen are 0 in the system. And there is no pressure drop in the system, so going to design and parameters, pressure drop parameter user specified is 0. And now once after doing all these, if you have not specified this energy stream, then it will be converged. But since we want that the inlet temperature and outlet temperature should remain the same, so we can either specify it as 826.9 degrees centigrade and it will be converged obviously. But better way is to use the set tool in the system. So what we will do, we will delete it, and what we will do, we will select the set and we will click on it, and we will say that the target variable is product temperature and it should be same as that of the feed temperature. So it one is selected and accordingly it is okay. And in parameters, the multiplier is 1, y is equal to x, and there is no offset. If you want some offset of like 5 degrees centigrade, then you will specify 5 over here, and accordingly it will adjust it. For example, you want a difference of 5 degrees centigrade between these two continuously throughout your process, then it's better to use set tool and give an offset value of 5. So accordingly it will be adjusted. So this has been solved, and now we have to check whether our desired conversion is achieved or not. So what we need to do, going to this reactions in results, 57.43% conversion of ethane has been achieved in the process. So it means we have to vary the reactor dimensions in the process because we have specified the kinetics. We cannot change it. We can only change the reactor dimensions. So what we need to do, either we can do it manually or we can use adjust tool, and that will give us our answer. So clicking on this adjust tool, placing it over here, what we need to do, adjusted variable obviously is the reactor length PFR 100, going down tube length, select, and target variable is PFR 100 conversion, and that should be 80%. Specified target value is 80%. And once we do, in going to this parameter, let's say we increase the iterations to 50 to avoid asking us about increasing the iterations. So start, and it has been converged, and you can see that after 8 iterations, you see at just one iterations 8, this has been converged. And if we go back again, this one is now 21.81. We have initially specified 10 meters as the tube length, but it has converged on 21.81 meters. And in this reactions, you can come and see results is equal to 80% conversion. And in this reaction balance, you can see that ethane inlet flow rate is 1000 kg mole per hour and outlet flow rate is 200 kg mole per hour. While if you calculate the conversion, which is XA is equal to FA naught minus FA over FA naught, then it will give an answer of 80% if you calculate it manually. And the Aspen is also giving you this information. And in this worksheet, you can see the duty of minus 1.154 multiplied by 10 raised to power 8 kilojoule per hour is required to increase the temperature because it's an endothermic reaction. So in case of endothermic reactions, obviously you need to provide the heat to ensure that temperatures remain the same. Like if you would read my research article, which is on Ethane Dehydrogenation, again the process is same and you have to provide the heat to keep the inlet and outlet temperatures same. And accordingly, in design, we have specified the pressure drop of 0. You can even specify some pressure drop if it is requirement of the process. And in performance analysis, you can see that across the length of the reactor, the temperature, pressure, vapor fraction, duties are given, enthalpy, entropy, and all the information is given. Then accordingly, the flow rates are given, reaction rates are given, transport properties, which is viscosity, and accordingly heat capacity, surface tension, etc. all are given. And accordingly the compositions, molar flows are given over here, and you can change it to mole fractions, and accordingly you can see that across the length of the reactor the mole fraction change, you can observe it as well. So that's how you simulate, and accordingly you have designed, because this is the final design of the reactor which you have done using Aspen HYSYS. So that's it from this video. Thank you so much. Please do watch, like, share the video, and subscribe to the channel. Also click on the bell icon to get all updates related to this channel. Till then, it's goodbye. Stay tuned for more videos.